Thanks. First, let me thanks for the CASP organizers giving me such a great chance to present my work at this competition. Uh, my uh, my work is mainly focused on predicting the RMSD or affinity of the protein ligand complexes using graphic transformer, and I'm from uh, SIAT, Shenzhen, China. For the content, I will include three parts. First is the introduction. And in this competition, I have developed three models. First, the S-graph RMSD was used for predicting the RMSD of doctored proligand complexes, uh, which is to choose the native-like compounds. And the second was using for the other task is to predicting the affinity, especially when the complexes are not available. We using separate graph for the pocket and ligand. And the last one, when we have an experiment is crystal structure or we have a doctored structure, we try to predict the affinity based on this given protein ligand complexes and hope it will be more accurate or at least provide more information. Uh, then we go to this slide. So want to show the model developing process. Uh, this is the graph IMSD building process. First, we uh, preparing the training data. We downloaded the PD protein ligand band, li protein ligand pairs from the PDB band, and using UniDoc for each pairs, we have a doc around 100 to generate 100 confirmations, and finally we got 100 once 1 million about 1 million for training and about 50K for testing. And importantly, we remove those doctor values and those RMSD value exceeds the 5 angstroms. After we got this data set, we transform this data. We extract the pockets around those ligands. For example, using a cutoff, I think it's one nanometers away from the ligands as a pocket. And then after we got the pocket and the ligand, we convert it into the graphic representation. And as what we do here is we using a single graphic to represent the interface information. And for the nodes, the residue nodes was using vectors to represent the vector, and we also using vectors to represent the atom nodes. And the spatial information was using the age to represent. Finally, we got this training data set, and then we use the RMSD value as the label. Then we were trying to construct a model. This is inspired by our previous work. We previously using GCM models to train such a graphic, but not this time we improved by the graphic transformer. And after we training, we got a model that can predict RMSD. Then we finally we used for this competition. And in this competition, we have several steps. The first step we using current available some best current available models to first AlphaFold 3 to online versions to build the protein structure, and then we using cofactors to find the pocket, which is from Professor Zhang Yang's lab, which is very great. And then we using to the UniDoc developer by other researchers to generate the confirmations. And finally, we using S or developed S graphic MSD to select confirmation candidates, and then we can using this for later applications. For the graphic RG model architecture, we also developed for this affinity prediction model is inspired by our previous week work, and the only difference, the only improvement is the transformer part. I think it is very suitable for predicting those protein ligands if we only know the binding site, but not quite sure the exactly binding position. For this S-graph affinity model, we have first using the PDB binder database and leaves the core set as a testing set. Then we preprint the graphic same as S-graphic MSD, and then we training, which process is highly similar to the graphic RG. So this is the model development process. And so finally, we got some results. And the first result, we rely highly on some methods developed by other scientists. For example, we use the AlphaFold3 online version to predict the protein structure, which is highly accurate, except some not so important regions may be predicted as a loop, but the core regions is almost overlapped with the experiment structure released later. And we using the cofactors to identify the potential binding site. And we can find that the binding site is the potential ligand, the predicted ligand, the predicted cofactor is have a highly similar position, binding position with the crystal ligand structure released later. We see this in these four cases, the four protein cases, and we for the testing performance during the S-graphic MSD, we have observed its convergence very quickly around the 20 approaches. So compare with one, because we rely on the traditional method, UniDog. So we want to see whether our method is really have an improvement, some experience over the traditional one. So we selected the data for a faster evaluation. We have chosen all the data except those native structure we are bound to A and B, and then we also remove the AR4 data because they are more. It has contained several parts, and one ligand may be bound to A or B. So to avoid the confusion in analysis, I for the convenience analysis here and time limitation, I quickly checked the data set, and we found that for the top 5, when the top 5 predictions, we can see the all blue one is all results, and the yellow one is the UniDog results. In the cutoff, in the MSD value of 5 angstrom, or we have more predictions for at this region, and we can assume because the confirmation is larger, MSD value larger than 5 angstroms usually means the prediction is not right anymore, and it's not so important how much it didn't the MSD how large it is. So we just want to see the details of this within 5 instruments, so we can see the below. All models has a more better predictions, especially at 2 angstrom to 3 angstrom and 3 angstrom to 4 angstrom. Because we using five top performance to test this, and we want to know whether the top one prediction has a similar trend. And now we see it is really have such trend, very similar trend, and indicating our method can predict more correct confirmations. For example, here it has 74 correct prediction vs the Unidog which has 15 correct prediction at the top score. So we want to check which case is our S-graphic MSD is good at, and which is Unidog is good at, and we want to see whether there has some regions both the methods are not so good. Here is we quickly selected some cases. We found that first the case this complexes our method is performs good. For the top 5, we all have we have several very low MSDs. For example, the top 1 and the top 2 and top 5. Well, for the Unidog, because the Unidog scoring function is using Vina, so I write Vina here. It has all prediction. The top 5 is all not good. It is around 80, which is very far away. So the left part is shows all predicted confirmation with the native one, and it looks good. Then we also checked this L string 0061. This case, both methods perform bad, and I checked why this is so difficult, and I found that is iron-like very small ligand, and this may be very highly not specific ligand. It can bind to anywhere anything. So that's understandable. Both methods are predicted not good. And for this L1013, it is a case that both methods perform good, and we can. So for this case, maybe a traditional scoring function is the similar performance with our data-driven cases, and there is also very few cases that is Unidog perform good, but the S-graphic MSD perform not so good. Maybe because of this kind of data is rather in the training set. Maybe the training size is still not so large. And this is the RG graphic prediction result. We see even we haven't highly accurate structure information, the binding interface information, but the prediction still, I think, looks okay. It's a middle strength Peterson correlation. Middle strength correlation. And we have a check which can and which can't. We found the first 3 compounds, it has a highly accurate prediction compared to the experiment one. And I think from observation, it seems that these compounds may be highly frequently at a database, or it looks not so strange. But for the below 3.1, it's more challenging. Our model is not perform good at least 3 cases, and we can from our observation we can see that some groups are more challenging and more rare. Maybe that's because the data-driven strategy often encountered. If it haven't observed too many of them, then it can't learn the rules from this input. We also because in the stage 2 task, the organizer has give us a better chance to check the model or models or methods. We have obtained the crystal structure at this time. So previously I thought if we have a crystal structure, we should have a much more better results. We first developed a method called S-graphic affinity, to using the binding interface information to predict this crystal structure's affinity. But unexpectedly, the result is not so good as non-interface dependent. The R value has reduced a lot. So this may have some. So we want to check whether we can see the rules from the cases that can uncount. And we have checked those perform good and perform not so good, and it seems not we can't directly to judge whether it's some of it is perform not so good. I think this may because my model needs to improve, or maybe because of the single confirmation may not enough for affinity prediction, because ligand sometimes are a little bit flexible in the servant state, in the servant binding state. Maybe like some kind of MD simulation, it should have some trajectory has more confirmations. But I'm not sure. I need to explore this in future. So my conclusion is that on S-graphic, I'm still using the deep learning to help identify more accurate binding posts compared to traditional method. And I think it is a complementary method for posting native-like post finding. And we still need to know that we still have some challenges in many cases. And the second conclusion is that we can use only pocket informations without interface residue pairs information that can effectively estimate affinity. This is unexpected. And I thought this is not so perfect because it still lost some interface information, but still a current available choice in jog screening task. And after we have a better confirmation and end this information there, I believe it will continue improved. And the third conclusion is that S-graphic affinity, maybe single confirmation is not enough to accurately estimate free energy. And maybe small data set with complicated input representation and the model architecture may lead to some kind of overfitting. So here, I first want to thank Casper 16 organizers provide such an opportunity to check our method and let us learn a lot of our models pro and cons. And especially thanks to many helpers from those professors. And also I thanks SIAT's colleges. They have provided a lot of encouragement and assistance for this presentation. Also, many thanks to the developers of this wonderful software that I have applied in this work. And yes, thank you very much. That's all my talk.
Thank you. Thank you very much.
Thank you very much.
Any question from the audience?